Integrating data sets into models and using models to measure the next data is crucial in dynamically changing environment. Today we are talking about data-driven mean field type game theoretic models of COVID-19. Reproduction number. Basic SIR models. Data-driven MFTG models. What is a basic reproduction number? Our note tells you the average number of people who will catch a disease from one contagious person. If it is less than 1, the cases will decrease. If it is equal to 1, it is stationary. For more than 1, it grows very quickly. Here is a situation where each agent transmits exactly to 1. The number of active cases at a time is exactly 1. So, after 3 weeks, 1 gets a total of 1 plus 1 plus 1. Which means, 1 times the number of weeks since the first infection. Now, 1 infectious transmits to 3 others. In this case, the number of active cases grows as 1, 3, 9, 27. One obtains an exponential or a geometric growth at this early stage. But then, it may change depending on the responses of the people and the intervention measures. Our note depends on multiple factors: biological, environmental, behavioral. Serial time interval. Consider a population with 1,000 people. Let us start with 1 person infected. We first look at the case where the serial interval is 10 days. There are 6 infections in total after 10 days and 31 infections after 20 days. The last 25 new infectious people will infect 125 persons, which makes 156 infections the first month. The sequence of active cases becomes 1, 5, 25, 125. A total of 156 after a month. We divide the 156 infections by 30 days in a population of size 1,000. We now look at the case where the serial interval is 30 days. In this case, there are 6 infections in total after a month. If the serial interval increases, our note decreases. If the serial interval decreases, our note increases. Meeting rate. Exposure rate. The contact rate quantifies the number of people an infectious person comes into contact with. Our note is higher if there are more interactions with infectious. 3 transmission modes: coughing, sneezing, and surface contact. SIR. There are 3 compartments. S for susceptible, I for infectious, R for removed, which contains recovered and deceased. The evolution of each compartment can be described by a Markov chain whose probability law solves a basic Kolmogorov equation. The ratio between the transmission rate and the removed rate defines a basic reproduction number. The R note for COVID-19 is not known. Different estimates are under investigation. One way to estimate R note is from the data. How to read the data sets. Data point per day. Cumulated data point per week. Cumulated data point per month. From the moving average data set, we solve a basic optimization problem to learn the parameters beta and gamma. At this point, a basic machine learning tool can be used too. From the learned beta and gamma, we built a data-driven dynamics. Here the SIR becomes a data-driven SIR. There are some advantages of this SIR model. It is data-driven, it is compartmental, and it is easy to implement. However, it has severe limitations. It is homogeneous. It is not localized. It does not capture community spread. It is not context-aware. We next build a data-driven SIRD model in which R is split into recovered and dead. We also extend the model and include age, location, mobility, and economic status. We combine economic, food security, mobility and pandemic to build a data-driven mean field type game theoretic model. The decision makers are the individuals, the firms, the authorities, local, regional, state, nation level, and international rules. This makes a trilemma between pandemic, economic and food security. We can find a Pareto equilibrium among them. Multiple criteria are involved, and the importance of a criterion depends on the decision maker. The pandemic aspect is extended to more than 3 states. It includes testing, hospitalized and quarantined as well as untested infectious and untested deaths. The collected data set is shared by the authorities. We process the data and learn parameters by strategic deep learning. The learned parameters are included into the model. Then, a game theoretic analysis is conducted. Decisions is suggested. Here is an example of evolution of economic cost versus pandemic the first 90 days. The data-driven MFTG model takes in consideration the data inaccuracies and the measurement errors and time delays. The data-driven MFTG can capture multiple waves and multiple communities spread. It includes a pandemic layer, a local mobility layer, an air and ground transportation layer, travel restrictions, and on-site worked hours. For some countries, it is crucial to process the reported data by means of filtering and learn a meaningful trend with a smaller data set. One way to validate a new model is to test it from different data structures and shapes. This data-driven MFTG model has been tested successfully over 66 countries. The reported data should not be considered as a state measurement. It could be delayed, incomplete, partial, and noisy. Here is an example where the number of active cases is not a single line, not a single exponential and not a single Gaussian. Multiple spatio-temporal communities spread. Non-Gaussianity. Non-gamma, observed in more than 15 countries. We now visualize the evolution of COVID-19. We start with January 22, 2020. We plot the 25 most infected countries. This data can be normalized by country population. It can also be visualized as total deaths per 10 million population. There is clearly a temporal difference in the spread across countries through international travels and then local transportations and local exposures. One of the key aspects is the probability of the being exposed. And this is through a close contact with an infectious. From the official detection of the virus SARS-CoV-2, it became epidemic and then pandemic within 3 months. At this point, most countries have the virus circulating locally and several testing strategies have been used. Millions of people have been infected. Thousands deaths. Huge economic consequences. Food insecurity in many underserved areas. All these are coupled with corruption, which is another virus. Thank you.